Good morning to all. I am Mehul Sangekar. I'm from India, but I have been in Japan for far too long. And I'm currently working in Jamstack. I'm actually not a biologist, so this is my first any jellyfish related conference. So my work, I'm actually from robotics, underwater robotics background. Uh, but I'm working with Dr. Duga Lindsay, and we are trying to do more new imaging techniques for jellyfish. And I realized that some of the work we have been doing might be applicable to studying jellyfish blooms. So, yeah, listening to all the talks in this conference has got me a lot of new insight about how the jellyfish blooms can affect fisheries. I mean, I always knew about it, but some of the presentations have been quite phenomenal. Of course, I realized that large jellyfish are more easy to see, and there's work done on using drones and aerial mapping to see them. But what about really small ones? I mean, most of the work is done by taking samples, which is great, but can we complement it by using other imaging techniques, which can also help you to get some early warnings? So if you wanted to make a monitoring platform, how would you do it? What would you need? So I guess you would need a system which can be kept for a long time, and that would have to have low power. So some imaging technique which uses low power, you should be able to look at small objects, and if you really want to identify them properly, if you can see through them, through the internal structure, it will be even better. If you can get size, very nice, and if you can count them, count their density, even better, and then combine it to say, oh, there's going to be a jellyfish plume, or then alert people on the land saying you should go take your sample, so you should collect more data. So the things which we were developing in the lab were shadowgraphs. So I know shadowgraph technique itself is not a very new technique. It's been there for a long time, which, unlike a normal camera, it uses collimated light. So because the light is parallel, doesn't matter how far you are from the camera, you can always get the same size. Plus, because it's a backlight imaging, you can see through the animals. So we've already been developing some shadowgraphs in the lab, uh, low-cost ones, and we have been trying different resolutions. So this is the same mastikas. I don't know. I'm not biologist. I don't know the names. Sorry, but yeah, you can see it at two different resolutions, and you can see the details are quite different. But we developed two cameras right now which can record videos at 20 frames per second, and we tried them in Japan in collaboration with Tokai University. The two shadowgraphs, we put them on a frame, and to get where we were, GPS, and of course a CTD profiler, which can give you depth and the temperature, density, salinity, etc. And we deployed it off a small boat called the Hokuto to see what we get. And we realized, oh, we saw some very interesting things with the shadowgraph. Of course, and we can see large objects, including jellyfish and other planktons, etc. But we could also see particle plumes. Like you could see dense particle layers, layers with no particles. We could see mixing layers where there's a density change. And that was quite interesting. So other than just looking at big jellyfish in the shadowgraphs, you could also get some indirect information. So we saw that, okay, if you take all these shadowgraphs and put them along a depth profile, you can actually know, oh, exactly where the mixing layer is, or at which depth which animals are, etc. But this was done manually. So you went through all the frames of the shadowgraph and then find out where everything is, and you put it along a depth profile. But you can't keep doing that. And especially if you're going to do automated monitoring, that's impossible. So then we started thinking, oh, okay, maybe it's time to start working on a more smarter pipeline to go through the data. And one of the idea was to have a quick look at the data and try to see what is in the frame. Use something which is very low computation to do this. And the idea is to use something like an autoencoder. And the idea is very roughly, Videos use different compression for different frames. Something very complex gets compressed differently, whereas something which is not so complicated gets compressed differently. So we trained the autoencoder to look at different frames which have low particles, high particles, mixing layers, and big objects, and then made a model. So with, if a frame with any of these things came, it would extract features. And then we tried it on actual shadowgraph data. So the idea was the trained features which were extracted before in the model, the autoencoder would again extract features from the current frame and then try to match them and then put them and decide, oh, whether this frame is more closer to like a high particle frame or a low object frame or a mixing layer frame, or there's a big animal inside. So we could go through the video data more quickly and find out areas of interest and then group the data into different zones. For example, the previous depth profile, we could now split into high particle areas on the top, the mixing area, mixing layer, and then the low particle round very quickly. And then based on the different layers, we can analyze the layer further. For example, the layer which has high particle, we can do things like particle count. So for that, we also established an algorithm where we started extracting, finding out ways to remove the background from shadow graphs and detecting objects. Not very complicated, so they can not easy to run real time, but not too bad. And if it runs, but yeah, you can see on the left side is particles being detected real time, almost real time on a video. And if you have jellyfish, you can also see and track them. And of course, if you have big objects, then all the frames which had, all the group which had big objects, what to do with them. We decided, okay, if you want to classify them, then we wanted to do a more machine learning based approach, and which also helps in ecology, or if you have an invasive species, etc., you can find it. So to start with, we are using YOLO 8, and we started making a training set for AI. We have just begun, and we don't have so many images yet, but we started making training sets for Solmaris and Doliolitz just to see whether it will work on our shadow graphs with the background, etc. And we have our own annotation tool in the lab, which is called Squiddle, where you can load a video and you can annotate it. And if you have metadata, like your depth profiles, etc., you can load it along with the video, and it keeps a track of everything. So we tried the models on one of our videos, and yes, we could actually, it could pull out Solmaris and Doliolitz from the video. And if instead of putting it on the depth profile, we could put it on the time profile, thinking that if this was an underwater monitoring station, then as per time, you could see when the group changes. That means, I think I've made a mistake in the index, but you could see when there's a high particle area, there's a low particle area where there are no particles. And when there are high particles, you can see it can find you automatically Doliolitz and Solmaris. We only started with 2 now, but we are now expanding it to other animals as well. Yeah, and now what could you do with such a system? So if we could set up a monitoring system having multiple shadow graphs, we already have 2 with 2 different resolutions, but you could make them based on what target you're looking for. And based on the patterns or the groups which comes in front of the shadow graphs, like you can predict whether it's a animal, whether it's high particles, dense particles, and then use that, use the CTD, and then guess if there's going to be a plume or an event happening, and then alert the station. I think that will be quite nice. You could also use the shadow graph data as an input for other modeling techniques. Like I heard some of the presentations where you're using other techniques for guessing or predicting plumes. So you could use the shadow graph as an input for those as well. And now we are trying to make more AR data sets. So we have set up like a tank setup in our lab where we are going to try to get more samples and make our own training data with shadow graphs. Currently, there are a lot of groups working on data sets for visual animals, but not so much for shadow graphs. So we would really like to work with people who are shadowgraph data. And right now, the autoencoder is made to work with only 3 types, which is the um, low particles, dense particles, mixing layers. But we realized that we could probably train it to find even more subtle changes, so we can split the shadowgraph dive into more smaller details. And yeah, thank you.